Our next speaker is Toygun BASAKLAR, and he is a PhD student in the Department of Electrical and Computing Engineering at the University of Wisconsin-Madison. And he will be presenting his work on tinyMAN, lightweight energy management using reinforcement learning for energy harvesting wearable IoT devices.
Good afternoon, everyone. I'm Toygun. Today I'm going to present tinyMAN, tinyManager, the lightweight energy manager using reinforcement learning for energy harvesting wearable IoT devices. Thanks to the evolving low-cost and low-power sensor technology, and of course thanks to the tinyML community here, the adoption of wearable IoT devices leads to many low-level edge applications, and these applications include but not limited to remote health monitoring, entertainment, sports, and fashion. However, the widespread adoption of these devices is hindered, and it's mainly because the IoT devices have limited battery life due to their small form factor to be practical, and the batteries with higher capacities are bulky and are inflexible, and while flexible batteries have low capacity, and this small battery capacity limits the battery lifetime and requires frequent recharging. For instance, I myself started using this posture trainer and for about 3 weeks, and I've stopped using it because it needs recharging for like every day. So as users, we do not want yet another device to manage and maintain. And to address this compliance challenge, self-sustainability of the device is the key point. And these are the 3 pillars to achieve self-sustainability: wearable energy harvesting, energy management, and energy consumption. So reducing the energy consumption of the target device or the algorithms that are deployed on the target device is heavily studied, and it's the first thing that actually comes to mind. And recently, wearable energy harvesting solutions has emerged as a promising solutions to power these devices, and they should achieve energy neutral operation to maintain a balance between maintain a certain battery level without manual recharging intervention. And this energy neutral operation is achieved or is described as if the total energy consumed at a given period of time equals the harvested energy in the same amount of time. However, due to uncertainties of the ambient sources, such as light and motion, relying only on these energy harvesting solutions is not sufficient to achieve this energy neutral operation. So therefore, energy management algorithms are proposed to maintain a balance between maximizing the utilization of the device and minimizing the manual recharge interventions. And these management algorithms should satisfy these following conditions. They should incur low execution time and power consumption overhead. They should have small memory footprint, and they should be responsive to the changes in the dynamic environment, and ideally learn to adapt to such changes. To this end, we propose tinyMAN, tinyManager, a reinforcement learning-based, prediction-free energy manager for resource constraints wearable IoT devices. And it is lightweight, it learns on its own, and it enables energy neutral operation while maximizing the utilization of the device under dynamic energy battery constraints and energy harvesting conditions. So our framework is deployed in an environment that consists of a target wearable device and an EH source. This figure here shows the general flow of our framework. So basically, tinyMAN finds the optimum energy allocations that maximize the utilization of the device under some constraints, and our framework, our wearable device prototype that we developed in our own lab, houses a TI SoC with various sensors and a small flexible battery which can be charged through harvested energy coming from this energy harvesting source. And as an EH source, we create a data set. We make use of American Time Use Survey to collect activity and location information of 4,772 users. And we combine this information with some hardware measurements collected in our lab. And these measurements include light and motion energy from energy harvesters, And that's how we created this data set. And this data set is divided into 4 clusters here. And cluster 1, so from cluster 1 to cluster 4, for instance, for users in cluster 1, they tend to spend less time outdoors or tend to do less activity, but users in cluster 4, they go out more and they do a lot of running, walking, jogging, etc. And using this figure shows the hourly distribution of the energy harvesting patterns of these clusters. And basically this EH source in our framework make use of these distributions and generate varying energy harvested patterns per user within a cluster. So the battery energy dynamics is a function of these 3 terms here. The battery energy level at the at the start of time interval t, the harvested energy level at time t, and the allocated energy at time t. And we use an episodic setting in our framework where an episode corresponds to a day, and hence the capital T equals to 24 hours, and each time step in an episode corresponds to an hour in a day. And we can calculate the battery energy level for the next time step by using the battery energy level at the current time step plus the harvested energy at the current time step minus the allocated or consumed energy at the current time step. And our batteries has some physical constraints. It is bounded by between the battery capacity itself and some emergency reservoir energy, which serves as a backup energy at all times. And to achieve energy neutral operation, tinyMAN ensures that at the end of the day, the battery energy level should be equal to some target battery energy level, and we choose this target battery energy level as the initial battery energy level so that the device can maintain itself, basically. So the utility of the device is a useful output produced by the device itself. It can be accuracy or throughput or something else, depending on the application running on the device. And tinyMAN supports any arbitrary utility function. In our framework for this work, we use a utility function with a diminishing rate of return, meaning that if we have an infinite amount of energy that we can spend, this utility function bounds that at a certain level. And if we have, let's say, if we allocate less energy than this EA min, which is the minimum energy consumption of the device to stay in the idle state, then it gives negative rewards, and that means it punishes the agent or the algorithm itself. So again, recall that our goal is to maximize the utilization of the device under certain battery energy level constraints. But how do we apply these, like all these information that I mentioned, to a reinforcement learning setting in a reinforcement learning environment? So we develop an environment to enable the adaptability of tinyMAN by any device and any application. So for that, we choose our state space as a 5-tuple, current battery energy level, energy harvested during the previous time step, battery energy level at the beginning of the episode, the current time step, and cumulative EH energy harvested in the previous time step. And the actions in our framework are actually the allocated energies at every time step. And again, these actions are bounded between this EA min and the current battery energy level itself. So we try to maximize the utility of the device, and reward function should use that information, should use the utility. And we try to maximize the utility of the device under some constraints. And we have 2 constraints, these energy neutral operation constraints and emergency reservoir constraints. And these constraints basically can be imposed by the reward function itself, so that the tinyMAN agent learns to maximize the utility of the device while satisfying these 2 constraints. And this equation shows how we impose these constraints in the reward function. So using all these information, we develop our environment in Python, and we register treated it as an OpenAI's gym environment so that any RL package can make use of it. So for the RL framework, so we first identify the characteristics of the device, the battery capacity, minimum battery energy level, and minimum energy allocations, and these are constant for the target device itself. And tinyMAN agent is trained separately on each of the 4 clusters that I mentioned in the EH source slide, and it employs a proximal policy optimization algorithm for training. So basically, so we first initialize policy and value network with random parameters, and at the beginning of each episode, we initialize the environment with randomly chosen initial battery energy conditions and randomly generated EH patterns using the hourly distribution of the cluster itself. And at each time step, we choose an action according to the current policy, and we collect samples, and then we obtain advantage returns or the value estimates using the policy and value networks. And using these, we update the network's parameters by calculating the loss function given in the proximal policy optimization algorithm. So the key point here is the generated EH pattern and the initial battery conditions are different for each episode, and that's basically how tinyMAN generalizes its behavior according to various EH patterns and different battery energy levels. So we compare our tinyMAN with prior approaches, and we also compare it with some unrealistic and unfair optimal solution. So this figure shows the allocated energy, the harvested energy, the actual, and the expected, and the battery energy levels for different solutions in a given day. And we give this example from cluster 2 because the users in cluster 2 represents an average person regarding the harvested energy in a given day. So as you can see, the actions that the tinyMAN are in correlation with the harvested energy. When the harvested energy increases, in the next time step, the allocated energy also increases, and when it decreases, again in the next time step, the allocated energy decreases. And as you can see here in this red curve, the red curve gives the optimal solution. So if the allocated energies are under this red curve, it means that the target device is underutilized. And as you can see here, the underutilization of the target device is less frequent for tinyMAN compared to other approaches. And this and the fact that it does not violate any constraints, the constraints that I mentioned, makes tinyMAN a preferable approach. We also evaluate its performance according to total utility obtained at the end of the day. So for that, we exclude 10% of the users in a cluster for fair comparison during training for testing purposes. We also evaluate it with 3 different network sizes. The number of hidden neurons in the hidden layers changes for these 3 different network sizes. We also evaluate it in 4 different initial battery energy levels. And this chart gives the comparison of daily utility values averaged over 4 initial battery conditions. And the total utilities for each clusters for all solutions is given, and also the cluster average is also given here. And as you can see, with a model size of 64, tinyMAN achieves up to 45% and 10% higher utility than the prior approaches. And it is kind of expected, but as the model size decreases, the utility that tinyMAN achieved also decreases. It's because the information captured by the network degrades with the decrease in model size. And also remember that from cluster 1 to cluster 4, the harvested energy increases. So for all solutions, we observe that utility increases as the harvested energy increases, because there is like more available energy on the device, so that the device can allocate. So we also evaluate the deployability of tinyMAN. So our wearable device prototype houses a TI microcontroller with an ARM Cortex M4 on it, and it has 352 kilobyte flash memory and 80 kilobytes SRAM. So we evaluate the deployability of our device using these three terms: execution time per inference, energy consumption per inference, and memory utilization of the target device platform. And we follow TensorFlow Lite Micro to convert and deploy our model on the target device. And on the target device, we measure the current consumption while tinyMAN is running on the device. And from current consumption, we calculate the power and obtain execution times and energy consumption per inference for different model sizes. Specifically, for a model size, the execution time decreases from 2.36 milliseconds to 0.75 milliseconds as the model size decreases, and energy consumption and memory utilization shows a similar behavior. But this reduction in these metrics also comes with an expense of lower device utility, so there's a trade-off there. So to conclude my presentation, we've discussed that variable energy harvesting solutions is not sufficient to achieve energy neutral operation and eliminate recharging requirements. And therefore, energy management algorithms are critical in that purpose. So we presented tinyMAN here, an RL-based prediction-free energy manager for resource-constrained wearable IoT devices. It uses the available energy, available harvested energy, to maximize the application performance while minimizing the manual recharge intervention and under dynamic energy harvesting conditions and battery constraints. It is easily deployable on wearable IoT devices thanks to its small memory footprint and low energy consumption per inference. And it can achieve up to 45% higher device utilization compared to prior approaches, and it easily adapts to unseen user-specific energy harvesting patterns and battery energy levels, which makes it a preferable energy management approach that can be deployed on a resource-constrained wearable IoT device. And as a future work, we plan to extend our wearable device prototype to log the harvested energy in a given day, and then using that information, we will implement an online learning functionality to tinyMAN. So I think this sums up my presentation. Thank you for listening.
Thank you. So what would it take to enable online learning functionality in your proposed method?
Can you repeat that?
What would it take to enable the online learning functionality that you mentioned in your conclusions?
Mm-hmm. Okay, so first we need to, again, log the harvested energy during a day, because the RL agent makes use of this harvested energy to update its network parameters, and we also need to implement the actual training on the device that we have not done yet. So that's the answer to your question, and it's a great question. Thank you.
Thanks.
So I see that you have two types of energy harvesting: motion sensing as well as solar.
Yes.
What is the ratio of these energies for a given, or in general, what you get?
What is the ratio?
What is the ratio? Like, which one is more effective? Is it solar energy is more effective, or motion energy?
Yeah, solar energy is like way more effective than the motion energy harvesting solutions. But since the device itself is actually gonna be weighed by the subject or the user itself, we make use of the motion energy too. So, but I mean, to answer to your question, yes, solar energy is way more effective than the motion energy. And actually, we have a poster in the poster session. My co-author is going to present that, and I think he mentions the difference between different modalities of energy harvesting
Thank you.
In the poster. Yeah, of course. Thank you.
When you show the improved utilization, have you quantified the overhead of the reinforced learning engine?
Yes, actually, these are the consumption of the reinforcement learning in action. So for the model size of 24, it consumes about 27 microjoules, and it decreases as the model size decreases. So these are the overhead of this our algorithm, tinyMAN.
Great.
Yeah.
Thank you.
Thank you.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Sentient. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Gravity, Hymix, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.